An action potential is a rapid change in membrane voltage that travels along a neuron's axon. It allows neurons to communicate with other neurons, muscles, and glands. An action potential begins when a stimulus causes the membrane potential at the neuron's trigger zone to reach threshold, usually around -55 millivolts. Once threshold is reached, the action potential follows an all or none response. It either occurs completely or it does not occur at all. Let's examine the stages of an action potential. First is the resting state. When a neuron is at rest, its membrane potential is approximately -70 millivolts. Voltage-gated sodium and potassium channels are closed, and no action potential is being generated. The sodium-potassium pump and ion leakage channels help maintain the ion concentration gradients across the membrane. Next is depolarization. When the membrane reaches threshold, voltage-gated sodium channels open. Sodium ions rapidly move into the neuron, causing the inside of the membrane to become less negative and then positive. This creates a positive feedback loop in which depolarization causes additional sodium channels to open. The membrane potential rises rapidly and may reach approximately +30 millivolts. Next is repolarization. At the peak of the action potential, voltage-gated sodium channels become inactivated, stopping the inward movement of sodium. Voltage-gated potassium channels open, allowing potassium ions to move out of the neuron. As positive potassium ions leave the cell, the inside of the membrane becomes negative again. Next is hyperpolarization. Voltage-gated potassium channels close slowly. As a result, slightly more potassium leaves the neuron than is necessary to restore the resting membrane potential. The membrane temporarily becomes more negative than -70 millivolts, often reaching approximately -75 to -80 millivolts. The membrane then returns to its resting potential. Leakage channels in the sodium-potassium pump maintain the sodium and potassium concentration gradients needed for future action potentials. Action potentials also include 2 refractory periods. During the absolute refractory period, the voltage-gated sodium channels are either open or inactivated. A second action potential cannot occur regardless of the strength of the stimulus. This helps ensure that the action potential travels in only one direction along the axon. During the relative refractory period, the membrane is usually hyperpolarized. Some sodium channels have reset, but the membrane is farther from threshold than normal. Therefore, another action potential can occur, but only if the neuron receives a stronger than normal stimulus. Together, these electrical events allow an action potential to travel rapidly and efficiently along the neuron's axon.